Tidal volume is the volume of air inspired or expired. At rest it is 500 milliliters of air per breath. For both trained and untrained performers, however, respiratory conditions like asthma can affect this along with gender, because males are generally on average much larger in size compared to females, and therefore more likely to have a bigger or smaller tidal volume. During some maximum exercise, tidal volume will increase and the thoracic cavity will decrease as external intercostals contract along with the diaphragm flattening and the sternocleidomastoid and the pectoralis minor contracting, forcing the ribcage and sternum up and out to increase tidal volume. During recovery period of steady-state exercise, tidal volume may maintain its constant state due to removal of waste products like CO2 within the muscles and to help with oxygen debt. But then will gradually decrease back to rest at 500 milliliters. Mo Farah uses altitude training to help develop his tidal volume. This occurs when he is training under oxygen debt, so his body has to take in deeper, a much greater volume of air per breath. Alveolar ventilation in athletes can increase from 70% at rest to 85% in total when exercising, and this is by having deeper breaths and only increasing the frequency of breaths only a tiny bit. Hemoglobin is the protein that carries your oxygen around the body. It's the amount of oxygen that joins with hemoglobin is determined by the partial pressure of O2. When oxygen forms with hemoglobin, it forms oxyhemoglobin. This occurs at the alveoli, whereby it leaves with 100 milligrams of mercury and depreciates as it goes through the body, depositing to respiring tissues like the muscles. The partial pressure of O2 in the muscle on the graph is at 15. So 75% has depreciated from the hemoglobin and allows diffusion of oxygen into the muscles. We call this dissociation of O2. The darker orange on the graph represents the partial pressure of oxygen at 40% is in the muscle tissue, and 25% of oxygen has been released from the hemoglobin. Ready for gaseous exchange. We call this that oxygen has been associated with the muscle to help with the dissociation curve shift. So more oxygen is associated with the muscle. We can help this by increased blood and muscle temperature to help speed up chemical reactions and gas transport. Aerobic system. Glycolysis take glucose from pyruvic acid. Pyruvic acid is made up of the enzyme lactate dehydrogenase, which is the catalyst for conversion of pyruvic acid into lactic acid. This process makes the muscles acid and fatigue, causing onset of blood. Lactic acid. To reduce this, coenzyme A has detected pyruvic acid, so it issues acetyl-CoA, and it turns into oxycetic acid and citric acid to reduce more oxalacetate acid, CO2, hydrogen, 2 moles as a result of resynthesis of the phosphate. Electron transfer is then initiated, where NAD and FAD collect the SS hydrogen ions to now form NADH and FADH. The Krebs cycle supports the continuous cycle. These molecules can now drop the hydrogen ions when in contact with the oxygen to form the non-harmful H2O water and 34 moles of energy through ATP synthesis. This can work upwards of 3 minutes, so it is suitable for steady state exercise. This should be the system used throughout the test. Proprioception is the sense of the body's position in space based on specialized receptors that reside in the muscles and tendons. The muscle spindle signals the length of the muscle and changes in the length of the muscle. These allow for smooth, coordinated movements during steady state exercise. When the muscle is stretched, this then activates the muscle spindle and sends this information to the CNS regarding the degree of stretch needed. The CNS must then decide how many motor units a motor neuron and skeletal fiber needs to contract to be able to correct the smooth muscle movement. The longer steady-state exercise goes on, the more effective the muscle spindles are at sending information between the CNS and motor units. Located within the tendons, the Golgi tendons are sensitive to any activity that involves stretching between the tendon and the muscles attached. Like the muscle spindles, the Golgi tendons send information regarding to the strength of the muscle to the CNS. Both the muscle spindle and the Golgi tendon work in conjunction with each other to make sure there is smooth movement during steady-state exercise. Breathing rate. We hypothesized that breathing rate would increase in correlation with intensity of exercise and duration. By measuring breathing rate, we can use the results to compare against other values like heart rate and ball rating to determine how intense the performer was working. To measure breathing rate, we timed 30 seconds and counted how many breaths they took in the 30 seconds and doubled it to get a breathing rate for that minute because we didn't have access to a Douglas bag. At rest, we expect 12 to 15 breaths a minute for an untrained performer, although during the test the performer reached a peak of 48 breaths in the 10th minute. That informs us he was working at maximal intensity and competing in the wrong zone with an estimated minute ventilation of 145 litres a minute. Heart rate. To measure the heart rate, we used a heart rate monitor to measure the beats per minute. We also used an oximeter to measure the O2 saturation within the blood, and this gave us the heart rate reading as well as a reliable Fitbit monitor. Prior to the test, we hypothesized that the heart rate would increase from pre-exercise resting heart rate from around 72 beats per minute, depending on levels of fitness, to 3 minutes. From 3 to 20 minutes, we expected results to show exercise targeting 70 to 80% heart rate max to enable the subject to work at a steady state for the remainder of the test, allowing heart rate to plateau and then decrease after several seconds to recover from oxygen jet to proceed to decline. However, at 10 minutes the heart rate was 187 because the subject worked at an intensity of 80 to 90% heart rate max within the first 10 minutes due to received rate of exertion being too high. Energy system. In our hypothesis, we suggested that the subject would use aerobic glycolysis as the main system for exercise to measure an energy system like creatine phosphate. It would be very difficult as there is no way for us to access equipment that measures the amount of phosphocreatine stores. Although we can measure the amount of lactate in the blood, which will give us an insight into the energy system used during exercise. And if it had any waste products like acid, then we can measure with a finger probe that drew blood for the blood lactate to measure to give a reading of the amount of lactic acid around the body. We measured lactate every 6 minutes and used an oximeter to determine if there was a change in the amount of oxygen within the hemoglobin. We expected an initial minor drop of O2 saturation, muscle spindles demanded for oxygen to steady state to 98 to 97%. Any O2 saturation less than 90% is considered low. The expected lactate result in was 7 to 10% lactic acid during steady state exercise. During the Exercise lactate reached a peak of 17.4%, which falls out of line with normative data due to the performer working in the lactic acid energy system, as there is higher concentration of lactic acid within the body. Conclusion. I believe I can accept my hypothesis of breathing increases up to a steady state, where the supply of oxygen and removal of carbon dioxide meets the demands of the exercise. Because 2 out of the 3 clients initially increased their breathing rate up to a medium frequency, and results showed breathing rate did not differ much, although we can't disregard some data from breathing rate, such as Josh's 6 minute, as it does not fall from outside of the range. I can further suggest that my cardiac output hypothesis of cardiac output increase from rest, but the increase will depend on the expertise of the performer. As an untrained performer, cardiac output will increase much faster and higher compared to a trained performer. It was questionable, and as the most likely to have the lowest aerobic capacity was Josh, and had a heart rate lower, and therefore lower cardiac output compared to a more athletic client, where he had a higher heart rate and higher cardiac output. I hypothesized blood pressure will increase initially, then decrease as arterioles vasodilate to aid blood flow. I cannot say that the results fitted with the hypothesis, as in the diastole phase and systole phase in pressure, results after the 12th minute were inconclusive, so would need more data to conclude on whether my hypothesis was correct between the 14th and 20th minute.